Hello everyone, welcome to another ALEKS tutorial. This is a kind of long one. This is about theoretical yield of chemical reactions. So this ALEKS problem gives us that we have butane in gas form reacts with oxygen, right, to produce carbon dioxide and water. And it says, what is the theoretical yield of water formed from the reaction of 4.65 grams of butane and 21.3 grams of oxygen gas? So, just for some context, the theoretical yield is just the calculation of how many grams of water you should have at the end of this reaction. The theoretical yield is to be compared to the experimental yield, which is something that you actually witness in lab as you do the experiment, and you compare this value that you get in lab to your theoretical yield to see kind of how accurate your experiment was. So with that being said, first thing I want to do is kind of, I want to get the molar masses. Let's write out like step one, because this has a lot of steps. So step one, let's call this find relevant molar masses. So, first thing I want to do, with these types of ALEKS problems, I hate it when they write it like this. If you add these up, you've got 3 hydrogen, 4 hydrogen, and 2 carbon, and another 2 carbon here. This just ends up, you can simplify this and write C4H10. It just makes the calculation a lot easier. So we also want to identify that butane, which is C4H10, and oxygen gas, which is O2, these are the reactants. And then those reactants are going to react together and form carbon dioxide and water, H2O. And these are the products. So we want to know that when we have this amount of butane and this amount of oxygen as our reactants, how much of the products do we form? So, as I said, let's find the molar masses. Now, by this point, hopefully you know how to find these. The molar mass for butane is going to be, from the periodic table, it's going to be the molar mass of carbon multiplied by how many of them there are in the compound, which is 4, plus the molar mass of hydrogen times the amount of them in the compound, which is 10. Hydrogen has a molar mass of 1.00784 grams per mole. This is according to ALEKS, and one thing to note is make sure you're being very specific in these problems, because there's a lot of calculations to lead up to your answer. And if you rounded this value to 1.01, you might get the wrong answer because you rounded too soon. So try to use the ALEKS values that are provided to you so you don't put in a lot of work for nothing. So our carbon is 12.0096 grams per mole according to ALEKS, and if we multiply those together, we get that the molar mass of butane is equal to 58.1168 grams per mole. And this is butane. Okay. So, sorry, I should label things a little better. This is butane. And then our second reactant is O2 gas, which is just going to be the molar mass of oxygen multiplied by 2, as this is a diatomic element. And so oxygen gas, according to ALEKS, is 15.9994 grams per mole. Multiply that by 2 and you get 31.998 or 9988 grams per mole. And this is oxygen gas. All right. What else do we need to find the molar mass for? Well, we're being asked for the theoretical yield of the amount of water formed from the reaction. At no point, so the only product we care about is water. We don't really need to find the molar mass of carbon dioxide. It's not relevant to this problem. So let's find the molar mass of water. Obviously, water is molar mass of hydrogen times 2 plus the molar mass of oxygen. And if you perform that calculation, you get 18.01508 grams per mole water. Okay. So now that we've found the relevant molar masses, let's move on to step 2. So step 2 is going to be write the chemical equation. Oh my goodness. Write the chemical equation and balance. So we have our reactants, which are butane and oxygen gas, and they are reacting to form CO2 and H2O. So that's going to be C4H10 plus O2 reacts to form CO2 and H2O. So let's just write out that basic chemical formula. So that's C4H10 plus O2 reacts to form CO2 plus H2O. Now we can clearly see right off the bat that this is not balanced. We have 10 hydrogens on this side and 2 on this side. We have 3 oxygens on this side and 2 on the reactant side. And we have 1 carbon and 4 on the reactant side. So, first things first, let's start with carbon. So let's add 4 to here, giving us 4 carbon and 8 oxygen there. And then we have 10 hydrogen over here and 2 over here, so I'm just going to write a 5 there. So that gives us that we have 4 carbon and 8 oxygen, and we have 10 hydrogen and 5 oxygen. So that gives us 4 carbon, 13 oxygen, and 10 hydrogen. So we can go ahead and write 13 oxygen here, but obviously this is O2, so this is not 13 oxygen over here. This is going to be 26 oxygen. So to compensate for that, we can just multiply everything by 2, except for our oxygen. And that will give us, just erase all this, that will give us 4 times 2, that's going to be 8. 5 times 2, that's going to be 10. And over here on the reactant side, that's going to give us 1 times 2. That's just going to be 2. So to double check, if we multiply this out, that gives us 8 carbon and 20 hydrogen and 26 oxygen. So as we can see here, 8 times 2, that gives us 16 oxygen, plus 10 oxygen, that gives us the 26 oxygen we have, and then 8 carbon and 20 hydrogen. I rushed through that a little bit just because this technically is something that you should have practiced pretty strongly by now. It should be second nature to you. But I just went through the calculation really quick just in case you guys needed a refresher. And so what finding this balanced chemical equation does is that it allows us to find our mole ratios, as in ration, the hell does that mean? As in, for every 2 moles of butane, we have 3 moles of oxygen, or 13 moles, sorry, of oxygen that will react to it to form 8 moles of carbon dioxide and 10 moles of hydrogen. So, that allows us to move on to step 3, which is going to be finding the limiting reactant or reagent. It'll commonly be called reagent on exams. And so what this means is that when we have 4.65 grams of butane and 21.3 grams of oxygen, one of those is going to get used up first. And whichever one gets used up first is going to determine how much of the products you will form. So the way we do this is I'm just going to write out reactants, and we want to find out how many moles of each reactant we start with. So let's start with butane, which is C4H10. So for butane, we are told in the problem that we start with 4.65 grams. So, if we write out a ratio here using the molar mass of butane we found earlier, we know that for every 1 mole of C4H10, we have 58.1168 grams produced. If you multiply this out, the grams cancel, and that leaves you with 0.08001 moles of C4H10. That's how many moles of C4H10 we start with. So that's our first reactant. Our second reactant is oxygen gas, O2. And in the problem, we're told that we start with 21.3 grams of oxygen. If we multiply that by the molar mass ratio, we calculated earlier that there are 31.9988 grams of O2 for every 1 mole of O2. If we multiply that together, the grams cancel, and we're left with 0.66565 moles of O2. So, now we need to look back at our balanced equation to find out which one of these reactants is going to run out first. We can clearly see that for every 2 moles of butane, we're using 13 moles of oxygen. So we can use this to form a molar ratio and find out how much oxygen gas will be produced by 0.08001 moles of butane. So, again, we write out a molar ratio. We write what we want on the top, which is we want moles of O2 gas produced. And we know that for every 13 moles of O2, we produce 2 moles of butane. So on the top, we'll write 13 moles of O2, and on the bottom, we'll write, for every 2 moles of butane. The moles of butane cancel, and you're just left with 0.08001 multiplied by 13 over 2. If you do this calculation, you find that you get 0.520065 moles of O2 is produced from this amount of butane. And this is really all the information we need, because we've discovered that from the provided amount of butane in the problem, which if we look back at the problem, they tell us that it's 4.65 grams of butane. That amount of butane will use up 0.52 moles of oxygen. Our starting amount of oxygen is 0.66565 moles of oxygen. We can see that this value is less than the given amount of oxygen, which means that our butane is going to run out first. This means that our limiting reagent is butane. If you wanted to double check this using oxygen, you can just set up the molar ratio the other way around. So you put the thing you want on top, which is moles of butane, and for every 2 moles of butane, you get 13 moles of O2. As with before, the moles of O2 cancel, and you're left with 0.66565 multiplied by 2 over 13, And if you perform this calculation, you'll be left with 0.102408 moles of butane. Notice that this amount of butane that this amount of oxygen produces is less than what you start with, right? So that means that oxygen is going to be left over at the end of the reaction. So hopefully that made sense. So that means that this value here is, it means that this value, this amount of moles, is what we're going to use to determine how many moles of our product is formed. So that brings us now to step 4. So step 4 can be sort of summarized as how much water is produced from our limiting reactant. And our limiting reactant is 0.08001 moles of butane. So how many moles of water is produced from 0.08001 moles of butane? Well, to find that out, we just need to multiply it by the molar ratio. Our molar ratio is, for every 2 moles of butane, we produce 10 moles of water. So we want how many moles of water we get, so we're going to put that on top. 10 moles of H2O is produced by every 2 moles of butane. Of course, the moles of butane cancel, and you're just left with 0.08001 multiplied by 10 over 2. If you perform that calculation, you get 0.40005 moles of O2. Now, that gives us how many moles of our product is formed, but we want the theoretical yield of water, which is going to be in grams. So all that means is that we need to multiply this by the molar ratio, or the molar mass, right? So for every 1 mole of H2O, we calculated that there will be 18.01508 grams of H2O. The moles of H2O cancel, and you're just left with 0.40005 multiplied by 18.01508, and that will give you 7.21 grams of H2O. And that is our theoretical yield. And that's it. Thanks for watching.